السلام عليكم ورحمة الله وبركاته. أحييكم محاضرتنا الجديدة. طبعا هذه حتكون lectures 6 and 7 يعني 2 lectures لأنه هي نفس الموضوع أوكي اللي هو protein kinase inhibitors، فلذلك حتكون 1 lecture. أوكي، حكينا بالمحاضرة السابقة عن signaling pathways وتطرقنا إلى farnesyl transferase inhibitors. Okay, so today we are going to talk about protein kinase inhibitors. So, protein kinases, what are those? These are enzymes that catalyze phosphorylation reactions on protein substrates. There are about 500 to 2,000 estimated protein kinases in a cell, okay, which is a lot. It's a large number of protein kinases, okay? Protein kinases are either present in the cytoplasm or present at the inner surface of the cell membrane, okay? And those are the protein kinases, the enzymes, okay? We have something that is called protein kinase receptors, okay? Those have dual role as receptors and enzyme at the same time. So they have a part that is outside the cell, okay, outside the cell membrane, which act as the receptor, and they protrude inside the cell to another part that is at the inner surface of the cell membrane, which is the enzyme part. Okay, they have found that overexpression of the protein kinases can result in cancer, or actually they found that some cancer types have overexpression of protein kinases, okay? And some of them have overexpression of the protein kinase receptors, okay? I think that's clear now. Okay, we have tyrosine kinases, serine threonine kinases, and histidine kinases, okay? And as the name imply, and I think now you know the naming of the enzymes, the tyrosine kinase phosphorylate tyrosine on some proteins, okay? It phosphorylates the hydroxyl of the tyrosine. The serine threonine kinases, they phosphorylate also the hydroxyl groups on serine and threonine kinases, while the histidine kinases, they phosphorylate the nitrogen of the histidine amino acid on some proteins, all right? All protein kinases, all of them, they use the adenosine triphosphate, the ATP, as an enzyme cofactor. So they take the phosphate group from the ATP and use it to phosphorylate the amino acids. And that's why they called phosphorylase sometimes, okay? Anyway, the active site, okay? We said that they phosphorylate protein and they use ATP as a cofactor. So the active site contains the binding site for the protein, right? And it should contain, or it have to contains the binding site for the ATP cofactor. The clinically useful inhibitors, they found that the clinically useful inhibitors, which means the drugs that are available in the market, okay, targets the ATP binding site. Okay, they did some studies on the protein substrate binding site, but they found that molecules that target the ATP binding site have better activity, okay, if compared with molecules that target the binding site for the protein. Okay, the ATP binding site, because all those protein kinases use ATP as a cofactor. So that's make the ATP binding site in all kinases similar, okay? But it is not identical, okay? It is similar, but not identical for all protein kinases, okay? That means there are some differences, like amino acid composition, okay? And we will talk about that later on, okay? But in general, the ATP binding site is similar. All right. This similarity but not identical, similar but not identical, allows for selectivity of inhibitor action. Okay, so as I mentioned, if there are some differences in the amino acid composition of the ATP binding site, that means some of the inhibitors will bind with some types of or some kinds or groups of kinases, but it will not bind to another. Okay, that will produce selectivity for inhibitors action. Okay, this pictures shows the ATP binding site as you can see it here. Okay, the purine base, the adenine base, there the adenosine, sorry, is buried deep into the binding site. Okay, so this is the beginning or the opening for the binding site. So this one, as you can see, is buried deep in the binding site. All right, purine forms two hydrogen bonding interactions to the binding site. Okay, also it forms some van der Waals interactions between the aromatic nitrogen base and the amino acids in the binding site. All right, the ribose sugar, this guy here, bind to what is called ribose binding pocket. Okay, this is the ribose binding pocket where the ribose sugar bind. Okay, the triphosphate chain, this one, as you can see it in the picture, lies along a cleft toward the enzyme surface, the opening of the active site, the door, the beginning of the active site. Okay, the triphosphate interacts with two metal ions and amino acids. Okay, so two metal ions, let me show you these if I can write them. Okay, if this is the first metal, okay, and if this is the second metal, all right, so the triphosphate will interact with those two metal ions. Also, it will interact with amino acids of the active site. I hope that you can see these. Okay, this one. Anyway, specificity surface, okay, we said there is some selectivity and specificity. So the specificity surface is an area of unoccupied binding site. If you can look at the picture, there's this empty area, okay, that doesn't have any interaction with the ATP. This is the cause for specificity. Okay, and which is, as we said, this area, which is an empty hydrophobic pocket, lies opposite to the ribose binding pocket. All right, and there is what is called the gatekeeper residue, which is an amino acid, this one, situated at the entrance, this entrance for the hydrophobic pocket. This one is important for selectivity and specificity, because if you have, they found that some kinases have big gatekeeper, okay? If the gatekeeper is big, it is gonna block the entrance, okay? Your inhibitor will not be able to get to the hydrophobic pocket, and that will hinder the binding of the inhibitor with the active site. Okay, as I said, the size of the gatekeeper is important in drug design and drug action. Also, the nature of the amino acid in the binding pocket is important to drug design because, as we said, this area is not occupied. So, and they found that the kind of amino acids in these areas, the unoccupied region, is not conserved, which means it is different from one kinases to the other, okay? And that is important because some inhibitors will be able to bind some of those amino acids and other inhibitors will not be able to bind to those inhibitors, okay? Anyway, the ATP binding site. Okay, this is just an enlarged picture of the ATP binding site that you can see the interactions of the purine. These are two hydrogen bonds with the backbone of the enzyme of the protein at a region that is called the hinge region. This is the ribose binding pocket, the cleft where the triphosphate lay down, and the hydrophobic pocket or the specificity regions. All right. The hinge region, this is just an enlarged region photo for the hinge region of the kinase target that shows the hydrogen bonding, the two hydrogen bonding, which means that any inhibitor should be able either to form 2 or 3 hydrogen bonding with the hinge region to be active. All right. There are kinds of kinase inhibitors, okay? And they have divided them into different types. Type 1 inhibitors act on the active conformation of the enzyme, which means that we have active conformation and inactive conformation of the enzyme. Type 1 acts on the active conformation of the enzyme, okay? Type 1 inhibitor bind to the ATP binding site and block access to ATP, all right? Type 2 inhibitors act on the inactive conformation of the enzyme, not the active one, but the inactive conformation. Type 2 inhibitors bind to the enzyme and stabilize the inactive form, which means it prevents the enzyme from going to the active conformation, okay? Type 2 inhibitors form additional interactions with regions of the ATP binding site not occupied by ATP. All right. Type 2 inhibitors are likely to be more selective. Why? Because it binds to those regions, and we said those regions are not conserved, which means the amino acids in those regions are different between one kinase and another. But there is a greater risk that random mutation to the target will weaken binding interactions and lead to drug resistance. Why? Because of the same reason. It's the same reason for selectivity. It's the same reason for drug resistance, because these regions are not conserved, which means enzymes might change those regions by random mutation. All right, other types of inhibitors, not only type 1 and type 2, there are other types which are currently being studied. Type 3 inhibitors bind to the inactive conformation, just like type 2, but these inhibitors are allosteric inhibitors. Why they call them allosteric inhibitors? Because they bind purely to regions of the active site not occupied by ATP. Okay, so type 2 binds to the ATP binding regions plus the unoccupied regions. Type 3 only binds to the unoccupied regions. All right. Type 4 inhibitors bind to an allosteric binding region that is not adjacent. It's not even near the ATP binding region. Okay, it's somewhere else in the enzyme. That's why they define them, or they call them type 4 inhibitors. While type 5 inhibitors bind in a similar way to type 2 inhibitors, okay, but bind to the active conformation of the enzyme. So if you remember, we said that type 2 bind to the inactive conformation. They found that type 5 bind in a similar way as type 2, but to the active conformation of the enzyme. Okay. Examples on type 1 and type 2 inhibitors. For examples for type 1, like the gefitinib, erlotinib, SU11248, siliciclib. These are examples on type 1. Examples on type 2 inhibitors, as we said, imatinib, nilotinib, sorafenib, and vatalanib. Okay. Weird names, right? Anyway, these are just examples on those inhibitors, and we are going to talk about them. And as we said, or as I said earlier, the type 2 are more selective than type 1. All right, this is going to be part 1 of our lecture, and we're going to keep going with part 2 in a minute.